Hello students, welcome back to the next lecture on dynamics. In today's lecture, we are going to continue our discussion on logistic model interpreted using the geometric approach. So, in the last lecture, if you remember, we arrived at this particular graph. This is dn by dt on y-axis and then n on the x-axis. We also figured out that when n is equal to 0 and k, dn by dt is 0. So, basically we know that this particular plot will intersect at n equal to 0 and at n equal to k. We also learned that when n is less than 0, dn by dt is less than 0. So, we learned that the plot, this particular plot that we will draw in this graph for logistic equation, which is dn by dt is equal to n 1 minus n by k, will be negative on left side of 0. Now, please pay attention, notice that I am making sure that the plot, that the trajectory intersects the x-axis at n equal to 0. And the reason is because at n equal to 0, dn by dt is 0. The y-axis is 0. We also know that this trajectory, this graph is going to intersect x-axis again when n is equal to k. We also know that this particular plot is going to intersect the x-axis again when n is equal to k, because when n is equal to k, dn by dt is 0. And there is no other way for this to happen except if dn by dt is positive between 0 and k, and then it intersects again. There are other possibilities too, but we will discuss them later. Here I just want to introduce you to a general geometric approach in case of logistic growth model. So, now let us look at this graph. We are going to use this particular graph that we have created to understand how the behavior of n changes with time. So, I am plotting n on y-axis and time on x-axis. So, let us say we are starting with original value of n naught, the initial number of bacteria. So, remember I am going to write 0 here because 0 is also a point where dn by dt is 0 and the plot intersects the x-axis. Now, if you just look at this plot, this is sufficient for us to understand the behavior of n with time, even though this plot is not sufficient to tell us what will be the exact amount of bacteria at a given time if we know the initial count, but it will help us understand how the bacterial colony, the bacterial population is behaving. So, let us use this to plot n versus time, which is what we want, right, but in a qualitative way. So, when I plot n versus time, you should not expect exact values here, 10 to the power 4, 10 to the power 8, no. We are looking at qualitative approach. So, let us say we are starting with n naught between 0 and k. Let us take this situation. I am going to use a different color for this situation, for this initial condition when n is between 0 and k. So, let us say I am starting from here, right, this is my n naught. Now, here I will plot my n naught at time t equal to 0. Now, if you look at this particular graph, this graph, which is helping us with geometric approach to this model, notice that dn by dt is positive, which means n will increase. If dn by dt is positive, it is telling me that n is going to increase, which means from here n is going to move towards the right direction, not towards the left. It is not going to stay stationary, it is going to move towards the right direction, which means n naught is going to increase, n is going to increase from n naught to some particular value as time progresses. Now, notice here, because I very strategically place the n naught to the left of this peak, as time passes, let us say t1 time passes and we reach here n t1, dn by dt now is even bigger than what it was at time t equal to 0. So, basically at t1 the slope will be even more steep. Are you noticing? This is very similar to what we saw in exponential growth. When n is increasing from n naught and it is still to the left side of the peak of this curve, the growth looks quite similar to exponential growth. So, let us say we reached here at time t equal to 0. So, here our number is nt2. So, not t equal to 0, at t equal to 2. So at time t is equal to t2, we reach at a population of n t2 here. Notice that dn by dt has maxed out, it has peaked. So here at this particular position, the dn by dt, the slope of this particular, the second graph, would be most steep. Now as we move further in time, and let us say we reach here at time t equal to 3, and now the population is nt3. So at time t equal to t3, dn by dt is still positive. So you notice the bacterial population is still going to increase, but the magnitude of dn by dt has reduced from the peak, which means the slope here at t equal to t3 will be not as steep as it was at t equal to t2. So we are still seeing a growth, but now the slope is again returning back, it's becoming less steep. Now if I move further at time t equal to 4, time t equal to t4, bacterial population is nt4. Notice dn by dt is so much smaller than what it was at time t equal to t3, at time t equal to t2, and at time t equal to t1. So at time t equal to t4, the bacteria is still increasing because dn by dt is still greater than 0, but the dn by dt is much smaller. In this graph, in the second graph, dn by dt is the slope of the curve. So at time t equal to 4, the growth would be very much flattened out. So notice what I shared earlier, we are already getting an S-shaped curve. As the time increases, let us say we reach time t is equal to tk, and I have very strategically written the word k here, the alphabet k here, because this is when n tends to k, when n reaches k. When n reaches k, what is dn by dt? You are right, dn by dt here is 0. So when dn by dt is 0, it means that whenever the n tends to k or tries to reach the k, the rate at which n is changing will slow down eventually to become 0. So this particular curve, this particular slope will slowly slow down to become horizontal flat. And this will happen when n is equal to k. So even without solving, just by plotting this first diagram, I am able to understand the behavior of bacterial population that follows logistic growth. First, the growth looks exponential, and if you look at this graph, there is a particular section where the growth looks linear, and then it slows down, which is characteristic of logistic growth. Now there are few questions that this geometric approach is not answering. First question is, when does the growth peak? Where will this peak lie? If we look at other growth like Gompert's growth, the peak looks slightly different than in case of logistic growth. So for that we need quantitative approach, which we are not going to use today. But I am going to explain to you some very important terms that are essential for us to understand before we move on with geometric growth. So let's look at these two plots that I have. The first plot is plotting the rate at which thing is changing for one-dimensional model versus the variable that is changing. In this case, this particular plot that I am drawing here, this blue line here, shows me the rate at which the n is changing at any given time from minus infinity to plus infinity. It helps me understand everything I need to know about the behavior of the system at any given value of n. Such plots, this blue plot that we have done, are known as trajectory. It helps me understand how n is changing regardless of time. Notice there is no time in this graph. This particular graph, which is independent of time, remember in the first few lectures I talked about autonomous system and non-autonomous system, and why when time is included it becomes very complicated to solve. So this particular graph, the first graph we draw in geometric approach, does not, it eliminates the axis of time. We are only looking at the variables that are changing, and if we have only one variable that is changing, then we look at the rate at which it is changing. That's how we plot it. So this blue line here is the trajectory, It tells me how n is changing. Let's say I know bacterial numbers can't be negative, but if the same logistic model is used for something that indeed can be negative, then I know how, in let's say here n is less than 0 at any given time, then I know dn by dt is less than 0. So I know that the n is going to move towards left side, it's going to reduce. If dn by dt is positive, I know n is going to move towards right side, it's going to increase. Here also n is positive but it is bigger than k, dn by dt is negative, so n is going to reduce. So this gives me qualitative information regardless of time for any given value of n. These kind of graphs are known as phase portraits. Phase portraits inform me about all possible solutions, qualitative solutions to my system, whether it is one dimensional, two dimensional or n dimensional system. Of course, in this course we can't go beyond 3-dimensional, there are limitations, but we are going to use the same approach to understand all possible solutions regardless of how time moves for systems that include competition, cooperation, predation, and in fact any system that can be modeled using ordinary differential equations like spread of epidemics, spread of diseases in population, how different chemical species compete with each other in water bodies, how disinfection takes place, all of them we can approach them qualitatively. Now, you know what a phase portrait is, that is very important. Phase portrait is the graph that tells you about all possible information for your system regardless of time. Trajectory is the path that your system takes. Trajectory is the path through which your variables move. In this case, there is only one variable, and this trajectory tells me how it's changing as n changes, regardless of how time moves. The other thing you need to understand is these special points where dn by dt is 0. If I'm starting at the special point when dn by dt is 0, let's say this is where I'm starting at t equal to 0. Since dn by dt is 0 at t equal to 0, there will be no change. So n will always remain here. Let's say t equal to 0, I am at n equal to k. Now t1 time has passed, I am still at n equal to k and my velocity is still dn by dt equal to 0. So these are the points where we do not see any overall change in the system, and these points are known as fixed points. So another very important term for you to know, fixed points. Fixed points are points where you do not see any change in the system. These are points that you must be familiar with. They go by the name of equilibrium. So if you remember chemical equilibrium, we are going to solve some equations when we deal with 2-dimensional and also 1-dimensional models, where we are going to use chemical reactions, for example autocatalysis, and we are going to model them and interpret them using geometric approach and understand how geometric approach is often sufficient for us to troubleshoot many of our problems. So equilibrium is when there is no net change, and these are those points, dn by dt 0, all your variables are static, but they may not necessarily be static, but overall they are static. There are two kinds of fixed points. Here we have two fixed points, so let's look at both of them. They are different, they are not same, even though dn by dt is 0 in both of them. I'm going to clean up the screen a little bit for you, and then I'm going to explain how they're different and what they're referred to as. Alright, the slide is clear now. So let me explain to you the difference between two fixed points, 2 points of equilibrium on the logistic curve. So here we have dn by dt on y-axis, and here, and this is our curve, and here we have our curve, and there are two fixed points, n equal to 0 and n equal to k. These are the two fixed points when dn by dt is equal to 0. And if you remember, fixed points are points of equilibrium where the rate at which things are changing becomes 0. So they are points of static, no change in the value of your variables. Now let's look closer to n equal to 0. What's happening around n equal to 0? I am going to use a different color for this. So in the neighborhood of n equal to 0, if I, let's say, start from n equal to 0, so n naught is equal to 0. As I mentioned, this is a fixed point, the point is not going to move. N will always be equal to n naught, which will always be equal to 0. However, let's add some perturbation to it. Let's add some change to it. So if instead of starting at n, let's say we are starting at n not equal to 0, but let's say I cause a negative perturbation. I change the value of n slightly to the left hand side. So what I am doing is I am moving epsilon units to the left. Epsilon here is very small, it tends to 0, right. So very small perturbation to the left side. So now instead of being at n equal to 0, I am at n equal to minus epsilon, 0 minus epsilon. Now what happens here, notice dn by dt at n equal to minus epsilon is negative at n equal to minus epsilon, right. So dn by dt is negative, which means things are going to move towards the left direction. N is going to reduce, and as n reduces, it moves towards minus infinity, towards the left side of the graph of the x-axis. So let's say I have introduced this very small perturbation to the left side, epsilon. As a result, n will reduce even further. Now let's say n has reached here after time t1. After time t1, it has reached here. Notice dn by dt has increased in magnitude, but it's still negative, which means n is going to decrease even more, and it's going to decrease faster than it did when n was equal to epsilon. So I'm going to move further to the left. By the time n reaches here at time t equal to t2, dn by dt has increased even further. So what this is telling you is that as long as n equal to 0, n will stay 0. The moment n reduces even slightly less than 0, it moves towards minus infinity, and there is no stopping it. So slight perturbation to the left, the value continues to move away from 0. This is an unstable fixed point on the left side, because the moment I introduce a small perturbation, it starts moving away from the fixed point. Now let's look at what happens on the right side. I'm going to use a different color for right side to distinguish between the two. So let's introduce a positive perturbation. So now I am going to take my n at n naught plus epsilon. So I'm positive perturbation to the right. So here I am at n equal to epsilon, positive epsilon. Notice what is your dn by dt? It is positive. At this particular situation, dn by dt is positive. What does it mean? If your dn by dt is positive, your n is going to increase, which means this particular point at n equal to epsilon is going to move towards right side. And as it moves towards right side, so let's say it reaches here at time t equal to 1, now dn by dt has become bigger. Now because dn by dt has become bigger, it is speeding away from the fixed point. So look at this nature of this particular fixed point. As you move even slightly to the left or right of this fixed point, the variable speeds away from it. It's moving away on the left side if you introduce perturbation on the left. If you introduce perturbation to the right, it moves away in the right side direction. This is an unstable fixed point. So as long as the object is sitting on the fixed point, it will remain there. But the moment there is a slight change, it will move away from the fixed point. Now let's look at the second fixed point. I'm going to use a different color. So now we are looking at the second fixed point, n is equal to k. Again, if I'm starting at n not equal to k, dn by dt remains 0. The n value does not change as time moves on, whether in past or in present or in future. But what happens when I introduce perturbation towards the left? So now let's say from n is equal to k, I have moved n so that now it is k minus epsilon. Epsilon is very small, remember here too, epsilon is tending to 0. So I move slightly to the left, epsilon units to the left. Notice what is happening. Now dn by dt is no longer equal to 0. If you look at the magnitude of dn by dt, in this case it is quite small, it is not a very big number. I mean qualitatively it looks pretty small. However, it is positive. So when epsilon tends to 0 and I am perturbing to the left, I have reduced n from k slightly, dn by dt is positive, which means n is going to increase. So what's going to happen is if I move this n slightly to the left, it's going to increase. Increase means it's going to move to the right. So if I move the n away to the left side from the fixed point, it's returning back in the direction of the fixed point. right? It's not moving away from the fixed point like it did in case of n equal to 0. Now let's create a perturbation towards the right side, which is I'm going to go from n equal to k equal to k plus epsilon. So now we are going from n is equal to k to n is equal to k plus epsilon. So here I am at k plus epsilon, epsilon units to the right. Epsilon is very small, small perturbation. Notice what happens here. When I move from k to epsilon plus k, dn by dt is now negative. It's still not very enormous in magnitude qualitatively speaking, but it is negative, which means things are going to move towards the left side. So dn by dt is less than 0, n is going to reduce. So if I move n towards the right side, it's going to try to return back to the fixed point. Notice here, from the fixed point, on introducing perturbation, things try to return back to the fixed point. This is a case of stable fixed point. Now, you don't have to sit and analyze each point like this. There's a very simple method, and I'm going to show you the very simple method. All you need to do is draw the phase portrait. Remember, this diagram is phase portrait. Draw the phase portrait and then look at the sign of the trajectory. So this is your trajectory, the blue line here. So look at the sign of your trajectory. On the left side of this first fixed point, which is 0, the trajectory is negative. dn by dt is less than 0, which means in general, things are moving towards left side. If your n is anywhere on the left side of this fixed point, dn by dt is less than 0, and we are moving towards left side. Between 0 and k, dn by dt is positive, so basically things are moving towards right side. The flow is towards right side. If n is greater than the k, dn by dt is once again negative, so again the value of n will move towards left side. So now look at these particular arrows that I have made. This flow is towards left side, flow is towards right side, and flow is again towards left side. I hope intuitively you can understand what is happening. Here, from this fixed point, the n is moving away. The flow lines are moving away from the fixed point. This is an unstable fixed point. If you create a perturbation to the left or to the right, the n value moves away. Here, the flow is towards the fixed point, so this is a stable fixed point. All you need to do is look at the signs of the curve, of the trajectory, draw the arrows, and then you can very quickly classify which fixed point is stable and which is unstable. In the quiz for this week, many of your questions will revolve around identifying stable and unstable fixed point using geometric approach in different systems, in one-dimensional and maybe even two-dimensional systems. Okay, another thing. Notice I use the word flow. We are talking about change in the number of something, number of bacteria, number of something else, doesn't matter what. And I'm using the word flow. Things are growing, n is growing, increasing or decreasing. Where is the flow here? When we draw phase portraits, we actually are inspired a lot by dynamics that human beings can easily perceive. For example, the motion of fluid. And lot of the principles and behaviors that we notice in our dynamic models are quite similar to the motion of fluids, whether it is air or liquid. So the word flow is very frequently used here. If you remember, for civil engineers in this course, you might remember the flow lines that we draw when we are trying to show the flow of fluid through a conduit, through a pipe, through a channel. Very soon in the upcoming lectures, we will similarly draw flow lines around the models to understand how things are changing. Because this is a one-dimensional model, our flow line is also in only one dimension, which is x-axis. So our flow lines are horizontal, and we know that on right side of n equal to 0, the flow line is pointing towards right side. On left side of 0, the flow line is moving towards the left, unstable fixed point. And around the n equal to k fixed point, the flow lines are moving towards the fixed point. And notice this is a one-dimensional model, so the phase portrait, the flow lines are also one-dimensional. This is a quite new approach compared to the quantitative approach that you have studied so far. So in the next lecture, what I want to do is I want to show you how we use the information we have gathered here so far on logistic model to plot n versus time, like we did for exponential growth model. That's all for today in this lecture. See you in the next lecture.